Hi, my name is Emily Wachowski, and today I will be deriving the heat diffusion equation in the Cartesian and the spherical coordinates. But first, I will be starting with the Cartesian coordinates. So first, I already drew a diagram, and so Qx, Qy, and Qz are all three of the heat flows entering the system, and then Qz plus dz, Qy plus dy, Qx plus dx are all exiting the system. And then within this, they're going to have energy generated and energy stored. So the first step in deriving the heat diffusion equation, we're going to write Taylor series expansion for the heat flows exiting the system. So the first one is going to be Qx plus dx, which is going to equal heat flow in the x plus partial derivative of the heat flow over x times dx. So this is going to be the heat flow in the x, which is going to, the heat flow in the x direction at some position in the fluid, and then this is how the heat flow changes when we move through the liquid in the x direction, and then this is the distance we are actually traveling. And then this all applies for in the z direction, the y direction too. So I'll write it out for those. So I wrote it out for in the y direction, it's the heat flow in the y direction times the partial derivative of heat flow in the y direction over the y, the change in y times change in y, and then same for the z direction. And then, so your next step is going to be writing out an energy balance. And so your energy balance, you're going to have your energy generated and your energy stored. So the energy generated is going to be equal to your heat flow times your volume, which is going to be dx dy times dz, and that's going to be in meters cubed, and your heat flow is in watts per meters cubed. So that way your energy generated is going to be in watts. And then your energy stored is going to, is going to be rho Cp times temperature, change in time, times also the volume, which is dx dy dz. And so your rho is going to be in kilograms per meters cubed, and then this, your rho Cp times partial derivative of temperature over partial derivative of time, that's going to be how your thermal energy changes as it's going through the liquid. And then times the volume, which is also going to be in meters cubed, so that's why it ends up being in watts for the units. So then from this, you can write out your energy balance, which is going to be your energy in plus your energy generated minus your energy out equals energy stored. So that's your energy balance equation, and then from this you are able to plug in from the previous, you can plug in, so I'm going to plug in before the Taylor series expansion just so you can see better on how everything cancels out and ends up simplifying. So your energy in is going to be Qx plus Qy plus Qz. And then energy generated, you take it from up here, and move it down to here. Q times dx dy dz minus your energy out, which is rho Cp times temperature over time, also multiplied by the volume. Oh, that's your energy stored, my bad. I meant your energy out, which is the qx plus dx. So minus qx plus dx minus qy plus dy minus qz plus dz, which equals rho Cp over temperature and time dx dy dz. And then from here, you can plug in the Taylor series expansion that I did up here, and it will cancel out the qx, qy, and qz since they both have that. And you're subtracting here and adding here, so it'll just cancel out. So I can write the simplified equation. And then you're still going to have your energy generated, which will be Q dx dy dz, which is going to equal rho Cp okay. And then from here, you can apply Fourier's law in order to simplify this more, which Fourier's law is going to be your heat flow equal to negative K, which is the constant, times the temperature gradient. So you can do this for Qx, Qy, and Qz. So it's going to be Qx equals, can you see that? Okay. Okay. And then it'll be negative K times your area times temperature gradient over change in x. And then this is actually going to be, so K times temperature over like the position, that's going to be, this is your heat flux. And you can, and then this is area. And you can also do that for NOY. So that is Fourier's law for Qx, Qy, and Qz. And then from here, you can plug it all back in. And then you can simplify, and then this will give you the simplest form of the heat diffusion. Well, not the simplest, but one of the simplest forms of the heat diffusion equation. So it would be so here is your final heat diffusion equation. So here you can see that for this, you were able to plug this in for Qx here, and then it simplifies out. So you are able to cancel out one of your dx's and go from here. So that was the heat diffusion equation was using the Cartesian coordinates, and then in the next part I will be discussing the spherical coordinates. So thank you.